All right, so today we're going to wrap up chapter three. Okay, so what I do want to mention here is right now we're about to start 3.6. And I do want to mention too that there actually are a few more sections here, but looking through them, I think that in the interest of time, what we're going to do is this. I'm going to have you read on your own the last three sections because they're just Eh, they're just miscellaneous topics, basically. They like to show you a lot of different applications. Some of these are physics applications and that kind of thing. But I think, and also, by the way, there's no assignments. If you look in WebAssign, for that reason, I chose not to put any assignments for these last three sections because I just didn't think they were important enough. We've got bigger fish to fry, so to speak. When we're done with this section, we really want to get into integration, which is chapter four, which is much, much more important. So, in other words, we're gonna have you, if you want to look through those, if you want, if you're interested. But there are no assignments for these three sections anyway, and they're not going to be on the tests. So I don't think we can justify spending any more time with them. So, like I said, if you're interested in those topics, you can read through those slides. But as soon as we're done with 3.6, we're going to dive right into chapter four. Okay, just because it's just so important and we really want to get rolling with that. So, I'll just mention here too, no questions on the exams from these sections either. So in other words, you're not going to be held responsible for them. Just, take a look, see if you find them interesting. If you do, you can go ahead and read through them. If not, it's fine because we're going to dive right into four, which is possibly the most important chapter in the book. So we really want to get to that as soon as possible. 3.6, on the other hand, is awfully important because they're going to give us a lot of very useful insights into the graphs of different functions. But it's not just the graphs, it's all the very important details that we can derive from looking at a function. So I think you'll find this section to be especially interesting and important because it's not just about the graphs themselves, but the details that we need to know to graph them properly. Some of it is review, of course, but some of this will help reinforce what we've seen so far. So I think you'll agree that what we're going to do in chapter 3.6 is very, very important. And then, like I said, when that's done, we can go straight ahead to chapter four, and you'll see why it's so important when we get there. All right, so here we go. Oops. So the title of this section is A Summary of Curve Sketching, but it's a lot more than that. Okay. It's not just practicing with curves. We really are going to deeply analyze several important functions and understand what we need to know, which ties together very nicely everything we've done up to this point. So now here they're showing us that, of course, when you look at a graph, one of the issues you run into is you've got to be careful not to miss any of the important details. Like every time we do something in Symbol Lab, you notice that it has a tendency to zoom in on it. And sometimes if you're not careful, you might miss some important details. So here what they're suggesting is that for this particular function, the graph on the right is the one we should be looking at because it shows more details. Okay, so with that being said, here's some key guidelines for analyzing any graph we may encounter. We always want to know the domain and the range. Okay, so let's just start writing these down. Um, Okay, so of course the domain and the range. What else might be interesting? Um, if there are any, let's look for intercepts, both vertical and horizontal intercepts. Okay. Um, asymptotes. And of course, here we might find horizontal or vertical asymptotes. Symmetry. Now, there's different kinds of symmetry that we may encounter. I'll make a list of them. We might have symmetry from left to right, from top to bottom, or more formally, with respect to the vertical axis. And so that would be, for example, y equals x squared. Symmetry with respect to the horizontal axis. Although in a case like this, you're going to wind up with something which is not actually a function, something like that. And then symmetry can be with respect to the origin. And that can happen in a couple of ways. Um, for example, so here with y equals x cubed, the first and third quadrants are mirror images of each other. And then we could also have this case. Oops. All right, let me fix that one. All right, well, it's not perfect, but it's a little bit better. This is y equals negative x cubed. And here the symmetry is between the second and the fourth quadrants, but they're both examples of symmetry with respect to the origin. Okay, so there's three different kinds of symmetry we may encounter. What else might we be looking out for? Um, yes, so derivatives. Of course, where f prime of x equals 0, there's are the so-called critical numbers. And each one of these may be relative maxima. And we also would like to know where f double prime, or the second derivative, equals 0. And these may be inflection points. And again, all that will give us clues as to how to draw this graph. Anything else? Or do not exist. I should include that too. I'll add that down here as a separate list. Okay, great. And um, and then of course look for 7. We'll put this as a separate category. Find extreme endpoints of inflection if they exist. Well, that kind of overlaps with the other ones, but that's fine. So this is what we're trying to do. Now, of course, not every function has all of these features. Of course not. So, but some of them do. Some of them might have all of these. So we're going to really inspect our functions very, very carefully. Okay. So now keep in mind too, this is how mathematicians were able to draw graphs before computers were invented. I mean, we're spoiled now. We can just go to Symbol Lab, but of course, throughout history, that wasn't the case. Here we go. Now, here, look at this function. It looks pretty terrifying. 2 x squared minus 9 over x squared minus 4. Now that looks like a nightmare. So let's cheat a little. Let's look at Symbol Lab first, just to see where this is going. Sometimes these functions, um, well, all right, let's see. 2 x squared minus 9 over x squared minus 4. Oh, for God's sake. I noticed there's something about the interface with this symbol lab. It can really be very awkward. You got to be really careful with it. All right. I think that's a 2x squared minus 9 over x squared. Good. Oh my God. Look at that. Ooh. Okay. So, yeah, there's a lot going on there, of course. So let's see what we can do. First, what about the domain? Well, of course, with the domain here, it's pretty clear that there's going to be at least 2 points where the function that would lead, I'm sorry, would lead to division by 0. So let's find them. All right, so either one of those would lead to division by 0. So we have to leave them out. And if you remember, this is how we write our domain in interval form. All right, so in other words, if you did this on the real number line, it would look something like this. You'd have a hole at the points that don't count. So that would be this piece, and this piece. And the round brackets indicate that those points do not belong to this domain. Now the range is going to be very tricky in this one. Um, you can see that it doesn't really include, here's the minimum point and here's the asymptote. Anything in between here is missing from the range. I'm not sure how they expect us to express that though. Um, I think what they mean for us to do is, all right, well, I guess what they, well, all right. So I guess what they're hoping that we'll do is say, we know that 2, we don't know it just yet, but would they expect you to figure that out? So yesterday we went through a list of rules for finding horizontal asymptotes. And so I guess we could go revisit that. But if you remember, there were th the rules dependent on the order or the degree of the polynomials in our ratio. And since this is really 2x squared minus 18, you might remember that the case where the second case, the degrees of the numerator and the denominator are equal because they're both squared. They're both second degree polynomials. Therefore, the horizontal asymptote, as you recall from yesterday, whatever day it was, um, is the ratio of the leading coefficients. So let's remind ourselves what that means. So that's the coefficient of the term with the highest exponent. So here there's an implied 1. So that would mean 2 over 1, which is 2. So the horizontal asymptote is 2, which means that the range will stop there, and then we jump up to that next segment, which you saw in Symbol Lab, where we have a minimum point on what looks like a parabola. And so whatever that minimum point is, whatever's in between that and the horizontal asymptote is missing from our range. So that means that they wanted us to find that minimum, relative minimum. Now, there's a few ways of doing this. What we can do to find that point is take the first derivative and set it equal to 0. Now, if you notice in the slides, it looks like they kind of cheated a little here. They didn't ever actually tell us where they got this range from. Um, well, I guess maybe they did. Uh, so, all right. Well, anyway, let's keep going here. Now, this is going to require the quotient rule. First, let's rewrite it like this. So, think of this as if you I think it's easier to write this as h of x is the ratio of f of x over g of x, and then h prime of x is uh, gx f prime of x minus f of x g prime of x all over g of x squared. Okay, so this is, of course, is our quotient rule. This is how we're going to find our relative minimum point. Okay, and let's copy this down here. We have 2x squared minus 18 over x squared minus 4. So based on the power rule, f prime of x is 4x. G of x is x squared minus 4. And again, based on the power rule, g prime of x is 2x. So if you plug all this into this expression, And then we divide by g of x squared. Now, keep in mind, our interest here is in finding out the values of x at which this expression is equal to 0. So we'll start like, let's do this. I'm multiplying or distributed the 4x across these two terms. So 4x cubed minus 16x minus, now here I do the same thing with 2x, 4x cubed minus 36x. So let's simplify it a little bit. And we'll end up with okay. So that means that if we set this equal to 0, we'll end up, we can cross multiply both sides by that denominator. So x equals 0 is one of the critical numbers or critical values. And if I plug that into the original function up here, let's see what I get. Okay, so on the top, this little bizarre piece up here, you're going to see the point 0, comma 9 halves. Okay. And what do we have? All right. And oh yes, and don't forget about the two vertical asymptotes because x equals 2 and negative 2 both lead to division by 0. We're going to have, man, look at this thing. So in other words, this parabola cannot fall outside this range. So in other words, the range is everything from negative infinity up to 2, not including the 2. It will include the 9 halves, though. Okay, let's make sure that's a square bracket. And that should take care of it. So now that was kind of a nightmare. Um, yeah, so that's where that came from. Now, the intercepts. Where do we get the x-intercept? Well, those are the points where y is equal to 0. All right, so let's go back and grab that original function one more time. We'll set it equal to 0. Okay, so the whole idea here is that we're looking at the points where this function equals 0. So I'll cross multiply both sides by that denominator, divide out the 2. Whoops. Add 9 to both sides, and I end up with, so those are my x-intercepts. Beautiful. Now, as you can imagine, the y-intercept takes place when x equals 0. All right, here we go. Let's try that. Now, of course, we just did that, but let's try it again. And that's our intercept. Okay. And we've already got that. So this is not only the minimum for the upper part of that function, but it's also the intercept. You can see why, because it crosses the vertical axis. All right. Wow. Is there anything else? Yes. So actually, we've already done this part ourselves. We got the vertical asymptotes and the horizontal asymptotes. Wonderful. Um, I don't think we wrote them down though. Oh no, there it is. We already figured that one out. The vertical asymptotes. Actually, I didn't specifically mention it here, but okay, that's good. So far we're all caught up. Now the symmetry, well, that is with respect to the vertical axis. Okay, so they did the first, second derivative, the critical number is 0, no inflection points. The test intervals are, let's see, what are they doing here? Oh, okay, so they just wanted us to see what this chart looks like. And you can see they have gone ahead and filled in um, the relative minimum point, and they've also included, because they took the second derivative, they showed us based on the signs where the function is concave up and down. Okay, so that's the only part that we didn't do. And so the way it works, if you remember, the second derivative, actually, where's the first derivative? Let's see what we can do. We should probably go ahead and solve for the second derivative just to confirm what they've done. God, where is it? Oh, I know it's here. Oh, here it is. This is the first derivative. So we set it equal to 0 because we were looking for critical numbers, but now we want to take the second derivative and see if we can identify for ourselves any points of where it's concave up and down. All right, here we go. Now, of course, this means the quotient rule again. And then, oh my God, well, G prime of X requires the chain rule. Um, all right, so we can plug all this into the quotient rule. Now, again, keep in mind that ultimately what we're going to do with this is set it equal to zero. All right. Well, we got a mess on our hands, but luckily this is our second derivative. So to find any potential, points of con where it's concave up or down, what we're going to do is set it equal to zero. So I can cross multiply both sides by the denominator. I can add one of these terms to the right-hand side. Then I can simplify to a certain degree. I can divide out 20s, for example. And what else can I do? I can divide both sides by x squared minus 4. And then I've got x squared minus, oh, okay. Now we're getting somewhere because I've got, how about this? How about if I subtract that from both sides? Okay, so then we have, let's multiply both sides by -1. All right, now we're coming up against a very interesting result here. Yeah, you can see what's about to happen. Uh-oh, x squared equals -4/3. Now, what this means is that, of course, we can't take the square root of -4/3. So that means there are no solutions here. So there are no points where the second derivative equals zero. So in order to find the intervals in which we're going to test for concavity, we're going to go back and use the asymptotes and the one relative minimum that we found. And then we'll test those intervals. Okay, so we set the second derivative equal to zero, and that establishes the points that enable us to create intervals within which we can test the sign of the second derivative. But here, those points don't exist, so instead we have to do something different. Okay, so that something different is we're going to use the asymptotes and relative. In this case, we found a relative minimum. And we're going to use those to describe our intervals within which we'll test the signs of the second derivative. All right, so if we go back, let's revisit these. Initially, way up here somewhere, we found that the asymptotes occurred, if I remember correctly, it was plus or minus 2. Wow, it was all the way up here. Yeah, plus or minus 2. And over here, we did find a relative minimum at 0. Okay. In fact, we can go back and look at the graph in Symbolab and confirm all this. Yeah, right here. So here's where x equals 0, x equals negative 2, and x equals positive 2. So now we can test the sign of the second derivative in those three intervals. Okay. So the intervals actually it's going to be more than three intervals. It's going to be negative infinity up to negative 2, negative 2 to 0, 0 to 2, and 2 to positive infinity. Okay, now, so the second derivative is up here somewhere. Yeah, look at this mess. So what you would do next is find a point within each interval and evaluate the second derivative. But in the interest of time, since they've already done this for us, I think we're going to skip that part and let's go look at the chart they've given us and write down the results. Only because this thing is such a mess and we know how to substitute. For example, if I wanted to do something in this interval, I could try f of negative 3, but why don't we just see what they've done already in the slides? Here we go. Yeah, so this chart already has everything set up for us. And so within the intervals that we've just defined, you can see what they did was they went ahead and they solved for the second derivative. And so here it turned out to be undefined. We had, well, that's one of our asymptotes, by the way. It was undefined here. But then they discovered that between negative 2 and 0, the second derivative is positive. And then here, between 0 and positive 2, it's positive again. So these are the intervals in which we have concave up, but the first derivative tells us whether the function is increasing or decreasing. Okay, so it's kind of unfortunate that they chose to give us such a messy example. I think it would have been easier to deal with a straightforward example, but I didn't write this one. But anyway, so these are all the steps we have to go through to fully analyze a function, and that in turn should enable us to graph it properly. I think they have another one in here that might be a little more down to earth. Um, yeah, see, they've got all the information right here. Yeah, what a mess. And so they want you to see all the details. We already identified the asymptotes, and we found the two vertical asymptotes. as well as the relative minimum. And so we really did a good job of finding all these details. It's still going to be tricky to sketch something like this, but at least we have all the information that we really need. But you can see there's quite a few details here. In fact, if I remember correctly, we were labeling these, numbering them, I mean, and what was it, seven? At least seven different things we need to test to fully analyze this graph. Okay. Well, anyway, so let's see what other examples they have for us. All right, now this one looks a lot more down to earth. That's good. All right, let's try this one. All right. And of course, as usual, we'll check Symbol Lab and see what it looks like. All right, here we go. All right, so let's go to Symbol Lab. We have the numerator is x squared minus 2x plus 4. And in the denominator, we have x minus 2. All right, very good. Now you can see we have at least one asymptote. Ah, oh my God. Look at that thing. All right, well, I guess by their standards, this is fairly straightforward. Let's see what we've got. All right, so what should we do first? All right, now I'm going to go back and consult with my list from last time. Here we go. So we should probably start with the domain and the range. Not that it's absolutely necessary to do this in any particular order, but sometimes, it helps to already know in advance what the domain and range are so you can look for points that might lead to asymptotes. All right, here we go. So the domain, as you can see, is not going to include positive 2 because, of course, that would lead to division by 0. Now, the range is going to be a little bit trickier because, as you can see from this graph, there's a gap in here between the relative minimum and maximum. So here you can see, and we'll find this in a few minutes ourselves, but here with the relative minimum, y is equal to 6, and here it's negative 2. So the gap in between is not part of the range. Okay, so the range is everything from negative infinity up to and including negative 2. Whoops, almost. I almost missed it. It's got to be a square bracket, of course, because that's included. And then we can start again with 6 up to infinity. Now, of course, it would be helpful if we knew where those came from. We'll get to that in a bit. So then if we're interested, we can look for vertical and horizontal intercepts. Okay. So let's remind ourselves that the vertical intercept of any function is simply the point where x equals 0. Okay, so we'll go back to the original function and plug in 0. All right, so of course, what we're actually doing is replacing all the x's with zeros. All right, so there's our vertical intercept, and we can confirm this down here. You can see that, yes, there it is. Um, Up here, if you notice, the function does not actually reach the axis. It only crosses here, okay? What about the horizontal intercept? And of course, keep in mind that this is simply where, now this time it's y that equals 0. So we'll set this function equal to 0 and solve for y. X rather, sorry, X. All right, let's try that. Now, if you look at this thing very carefully, you might notice something interesting. It looks like x minus 2 might be a factor of x squared minus x, 2x plus 4. Why don't we see if that's the case? Let's try to factor this. So in order to factor it, we need two constants whose product is 4 and whose sum is negative 2. Let's see if we can find two numbers that satisfy both of those requirements. We could try 2 and 2, okay, or negative, oh, maybe not. I guess not. I was thinking maybe we could do that, but it doesn't look like it. So, nope. All right, never mind. Sometimes it works, sometimes it doesn't. So instead, here's what we'll do. We'll just multiply both sides by x minus 2, and that reduces it to x squared minus 2x plus 4. All right, well, we have ourselves a quadratic equation here, but it doesn't appear to be something that can be factored. So instead, we can use the quadratic formula. All right, so let's remind ourselves how that works. All right, so just in case it's been a while since you used it, whoops, for C, for any quadratic equation, ax squared plus bx plus c equals 0, the values of x are minus b plus and minus the square root of b squared minus 4ac all over 2a. Okay, nobody forgets the quadratic formula. Okay, there it is. So in this case, as you can see, a is 1, b is negative 2, and c is 4. All right, let's try that. And of course, be very careful with the signs. There's a lot of opportunities here to make sign errors. All right, let's see what we got. Okay, well, we we do have an issue here. Guess what's happening? We're going to wind us up with a, we're not going to end up with any real solutions. You can see because I've got the square root of -12 here. So in other words, there aren't any x's that satisfy this equation, at least not real x's. And so therefore, there is no horizontal intercept. Wow. Okay. So they pulled a fast one on us again. No intercepts. You can see from the graph that there aren't any. All right. All right. So that's good. Asymptotes. Well, let's see. We've already seen there's a vertical asymptote at x equals 2. There doesn't appear to be a horizontal asymptote, though. All right. So that'll do. And that, of course, is because that leads to division by 0. Symmetry. Yes. Now, this is. That's actually no. I mean, yes and no. I mean, if you look at it, it's a different kind of symmetry than what we're used to seeing. It's um, it's not with respect to the horizontal or vertical axis. You can see that it's sort of slanted. In other words, um, you could flip the top graph over down to the bottom. And so what we actually have here is symmetry with respect to the origin. We also have something called a slant asymptote. What is that supposed to mean? Well, if you look here, this dashed line that Symbolab gives us, it's the line y equals x. Okay. And that's referred to as a slant asymptote. Okay. Because you notice that the function does not ever touch it anywhere along that line. Okay. So that's what this is all about. All right. What else are we looking for? Ah, critical values, of course. Now let's get to that. So first, we're going to take the first derivative, set it equal to 0. We can get rid of that split. Uh-oh, what happened there? All right. Well, it's for a second there, I thought I lost my work. Boy, that um oh my God, this looks very scary. Oh, I think we did lose something here. All right. Um, well, remember, this is where we determined that there was an asymptote. No, oh no, sorry. This is where we're looking for the intercepts. So yeah, I don't know what happened there. The problem here is that this handwriting is wonderful as far as it goes, but it does tend to take up a lot of memory, and occasionally the computer gets cranky about it, and that's what we just saw happening here. Um, I don't think there's anything we can do about it to recover it. But okay, so what were we trying to accomplish here? This is our vertical intercept. And then we discovered that there was no horizontal intercept. So we don't have to go through all of that again. So remember, the vertical intercept is where x equals 0. The horizontal is where y equals 0. And then we were looking for symmetry, and we talked about the slant asymptote. So let's go ahead and look at the critical values. All right, so we'll have to take the derivative of this function. Now, as you can plainly see, this is going to require the quotient rule. Oh my God, I don't know. That's a very scary sign when I better save that real fast. All right, here we go. All right, so remember how that works. If this is our setup, we have a ratio of two polynomials. Okay, so in this case, f of x is the numerator, and therefore f prime of x is 2x minus 2. G of x is x minus 2, and g prime of x is just 1. So we do all the substitutions. All that gets divided by g of x squared. All right, so let's clean this up a bit. All right, so I think we should simplify it. The first term can be solved for with FOIL. Oh, okay. Uh, this is left over from the other problem, isn't it? I didn't realize those were still down there. All right, let's do this. And then we have this. All right, so they can stay up there. And then we can get back to this. All right. And I'll be sure to save this at least every 8 seconds. just in case it happens again. All right, here we go. So let's multiply these out with FOIL. So FOI, and then last is these two, which is positive 4. So we have 2x squared minus 6x plus 4. And so that's the first part here. This x minus 2, 2x minus 2. So we have, and then we have this other quadratic expression, x squared minus 2x plus 4. And we're still dividing everything by x minus 2 squared. All right, so now we can simplify a little more. Now, eventually, we're going to set this equal to 0 and find the critical values if they exist. All right, so now we can start consolidating some of these. X squared minus 4x. These drop out. All right, so we set this equal to 0. So we are down to, we can factor out the x. Those are my critical numbers or values. All right, now let's look at the graph and see where they are. 0 and 4. Now 0, oh, there you go. What do you know? These are indeed the relative maxima and minima. With such a bizarre graph, it's hard to tell sometimes. In other words, these are the points where the tangent line is horizontal. Okay, we don't now, without looking at the graph, we don't know which one of these might be a relative maximum or a minimum, but we do know these are the critical numbers. So we can test them by doing well, we can do one of two things. We can use the first derivative test or the second derivative test. So why don't we do this? Why don't we're going to have to do this sooner or later anyway. We could take the second derivative and see what happens. All right, hold on. What do we have? X squared minus 4x over x minus 2 squared. All right, that's the first derivative. Now, the second derivative, of course, will be based on the quotient rule. So let's try that again. Think of this as f of x, g of x. All right, so now, of course, we have to plug these into the quotient rule. Great. Okay. Okay, and then g of x squared would be. All right. And of course, then you would set this equal to zero and solve for the inflection points. But again, you can see it's going to be quite a mess. So let's go take a look at the results they've got just to confirm them. Otherwise, this could take hours. I mean, really, come on. So yes, we've got the points that we need. Um, those were all the points where the second derivative. Oh, I see what they did. They simplified it to 8 over x minus 2 cubed. Okay. Hmm. And so their intervals are going to include, we have the critical numbers. We also have the asymptote. So basically, all they did here for these intervals was the same thing. They've got the critical numbers and the vertical asymptote, which is 2, and then they would have tested the sign of the second derivative in each of these intervals. And this is the result. Okay. So let's just copy this. And you can see that, uh, let's see, let's grab the picture of the graph too while we're at it. All right. So let's see, what have they done? So they're telling us that up to zero, but not including zero, the function is increasing, which it is, but it's concave down. And you can see why, because the slopes of the tangent lines are decreasing. Okay. But that also is why this is a relative maximum. And then at exactly zero, yes, we do have the relative maximum. Then from 0 to 2, the function. Oh, I see. They're breaking up again here. Like in other words, they treated this as a separate interval. Okay. And then at exactly x equals 2, we have an asymptote, so none of these are defined. And then between 2 and 4, we have, remember, this is 4. The function is decreasing, but it's concave up because it may seem strange, but the slopes are becoming less negative. And that's why we know that this is a relative minimum. And then after that, the function is increasing and it's concave up forever. Okay, so that's what this is all about. So, I guess they were trying to tie together all the key concepts, but, I think they could have picked some more down to earth examples, but this is what they're suggesting that we do in each case when we run across a new function, run through this analysis, pick out all the important details, and then we can take a shot at sketching it. So that's really what this was for. Anyway, I'm not sure how far they're going to take this in MindTap, or WebAssign rather, but this now I did mention, by the way, 3.6, there's also a 3, 7, 8, and 9, but I think it would be best if you read those on your own because there are no assignments for those. and they're not going to be on any of the exams. So those we can think of those as optional topics. If you want to read them, that's great because they're really just applications. There's nothing completely new in there. So what we're going to do the next time is we're going to start chapter 4, which is really maybe the most important chapter in the book. And I want to spend more time with that than this. So we're going to stop this here and we're going to go on to 4, where we're going to introduce, well, you'll see when we get there, maybe the most important concept in calculus. All right. So that's what we'll do next time we meet. So I'll see you then.